understand it. Just like when we go to Greece, when we go to Japan, when we go to Stockholm, we want to understand the beauty of those cities. Okay, but then we need to, once we see the beauty of the city, then we want to understand why, and perhaps the best way is to learn the language. Right. So when Stafura come to Taiwan, if you enjoy it, perhaps you'll start to learn a little bit Mandarin, so that you can enjoy more. So this is the same situation that if you see something that is interesting, then you learn the language and try to understand it. The handout give you, and also the textbook, give you a full derivation, but then I will just give you some concept so that you can read the details by yourself, okay? And the concept is a little bit abstract, just like the way you learn electromagnetic wave from a class. If you learn the electromagnetic wave from a class, you'll see that this obvious class up to this point has been quite intuitive. Okay? But then when we involve the electromagnetics, wow, then it's more like an extension of the electromagnetic class. All right, so we start from what? Start from Maxwell equations. Okay? And then Maxwell equations give you the wave equation. And then if we are dealing with harmonic wave, that is single frequency, sinusoidal varying, then we start from Helmholtz equation. And if you sort of put the problem into the Helmholtz equation, then we want to identify what the problem we want to solve. So what is the problem we want to solve? Well, physicists in the early days try to make this problem as general as possible, okay? As general as possible. So the scenario is like this. I want to determine the electric field at this location. I want to determine the electric field at this location. And of course, there's a light source, right? And if I know the electric field on the surface, if I have a knowledge of the electric field on the surface, can I determine the electric field at this point based on the source radiation? So this is the problem define the whole problem. Well, this is a configuration defines the whole problem. Why do we want to look into this? Well, look at this. We have a source. Okay, we have a source, and we have some aperture, and then we send laser onto it, and then you see something. That is the electric field you want to know. And this aperture defines the field on the surface, right? This is the surface, some surface, although it's finite. But physicists in the early days sort of model the problem with a full surface. If I know the surface field, can I construct a field here? Well, where do I get this surface field? From this point source, from this source. So this is the problem that we want to solve. Okay, is this clear to everybody? If you don't know why you want to do this, then you'll get lost immediately. So it's okay with you, the source, and then you want to get the field at this point, but then you have some aperture in between. You have some aperture in between. You have some aperture in between. You have some surface in between. You want to know the field over there, but then you have some surface in between. Okay? This is the surface in between. Okay. So this is the problem we want to solve. And then physicists manage to solve this problem. Okay, with a source and also surface embedded into this expression, coming out from the Helmholtz equation. Okay, so this is the electric field at this point, and then the source is inside, and then you have a surface defined by this one. This is not surface we worry about, okay? We worry about this surface. And then you have a spherical wave, suppose, okay? So if you have a spherical wave, then it's going to be expressed like this, ideally. Okay. Is there any question? And this rho is the radius between this surface and this source. And the coordinates is defined primarily for this surface. So everything is referenced to the coordinate defining this surface. And then you can do integration. Okay. Your origin is not here. Your origin is not here. Your origin defines this surface. Okay. Any question? All right, let's do some approximation because the wavelength of this guy is about submicron, very, very teeny. I'm talking about a distance that is meters. So I can do this approximation for sure. Rho is the distance between this surface point to this source. R is the distance from this surface point to the point of interest, rho R. Okay, and the surface normal is point outward to this surface, right? And because the origin is on this surface, so the direction of rho is point along this direction. Okay, the direction of R is point along this direction because the origin is on this surface. Okay. All right. So in the far field, this rho and R is much larger than wavelengths. It's reasonable. Reasonable. If we work with optics, this is usually meters, and this is submicron. Of course, this is much larger. This is all valid, so you can do a far field approximation. So diffraction theory is the sort of again a calculation arguing to what extent you to do an approximation. Okay, and it's a big struggle in the development of the theory. Okay, so if we adopt this approximation, then this is reduced to this expression. Okay, this dot n dot r n dot rho basically is the angle, projection angle of r on n, projection angle of rho on n. N is the some surface normal. But later on, we're going to simplify this configuration into this configuration. Okay, and this configuration is much easier. Why? Because the light source is going along that direction, and quite often when we look at this, we look at the dot. That is almost collinear. Okay, so it's not so general. In fact, we'll be looking into, well, more or less connect this to this point and put the surface down to this location to simplify the whole thing. So this is sort of generic and also the general situation. Now, if I have a almost collinear scattering, and will be along this direction, right? Surface normal direction. And my R will also be more or less along this direction. Okay. N and R will be almost along this direction. And for forward scattering, you have such a condition, right? Because they are collinear. Backward scattering, then you have pi. That is N and R R is this direction. Get it? Right? So basically you put this to this location. So everything becomes a single line. So N and R will be along the same direction. So this is the sort of forward scattering, backward scattering. For forward illumination means that my laser propagation is along this direction, and is also along this direction, but the origin is here. So my laser, if I put my laser here and put origin here, the vector low is going this direction. Okay. You see this? This is the aperture, right? And this is the origin. And then my source is here. So if I want to describe my source, I need to use a vector along this direction. Low, Sukai. Agree? Right? This is surface along this direction. But my source is here, but my origin is here. So this low is along this direction. The opposite of N, so you get minus sign here. Alright. So we call this oblique vector right here, determining how the surface is oriented with respect to the source and point. But later we're going to adopt this, much simpler for most of the experiments. Okay. So we'll be working with this, and then try to simplify this expression. So if you do a tile expansion on the distance versus the aperture of the coordinate up to the second order term, then we call it Fresnel diffraction. If we retain just the linear phase term right here, this is the phase term. So we start to do the tile expansion on this term. Okay. Do tile expansion on this term. If we retain the first order term, then we call it Fraunhofer diffraction. If we retain the second order term, then we call it Fresnel diffraction. That's it. So it's a struggle in diffraction theory. Right, so let's do the expansion. Define all the coordinates. S, P, but remember that the later we're going to straight this line, because this is the aperture. So this is surface. Previously, you have this small surface. Now, we just put the screen here and then drill a hole. Okay, so the surface normal direction is along this direction. There's a small angle with respect to R and also a small angle with respect to low. And then we have to define the coordinate system, the coordinate of everything. Set origin somewhere here on this screen, O. So from O, the source has a distance of low prime. And from O to the field point has a distance of R prime. Okay, but the aperture is right here. The aperture of the coordinate is defined to be a capital X, Y, Z. Or however you can put small x, y, z here. You can put the big x, y, z here. It doesn't matter. Just a label. Okay. So you define the coordinate of this aperture with x, y, z. In fact, in the next section, I'm going to put this big x, y, z here. It really doesn't matter. Okay. You just need to keep track of your definition. And for this source, let's put x0, y0, z0. Any question about this? So, okay, right? Just a definition of the coordinate. But then the origin is on this screen. Okay, we follow basically this construction. The origin is on this surface. And then there's a certain vector, surface normal, along this direction. Okay, later we're going to straight out, allow these two SOP on the same line to simplify the calculation. But now we just go for the most general setup. Right, so you can define, for example, this rho square from here to here. Well, this is simple, right? You take the two coordinates and do the calculation like this. Take here the R from here to here. You know this is x, y, z, and this is x, y, z, 0. So you do this calculation. You check. That's right? It's just the general calculation for the distance between two dots. No question. All right. Then let's do a paraxial approximation. Think about that. The light ray going through this aperture is more or less along the central line. So the angle is very small. The angle is very small. So this and this are almost co-aligned, but off by a small angle, delta. This delta angle, if you try to argue how big it is, basically this delta angle is the angle between this normal and also R. If you extend this along this direction, this angle is going to be slightly bigger than this one. If I have the line from the source to be like this. But if this S and P are more or less aligned, if this S and this point are more or less aligned, then this angle is going to be almost the same as the angle between this line and this line. So you see that the people really struggle with this calculation. Can you see it? Well, delta angle is this and this, between these two lines. Apparently, if you extend this along this direction, okay, this angle is not going to be equal to delta. But if you allow this source point to be more or less aligned with this P point, and we say, hey, we can accept it. It's just a small correction. So let's just put the data here. So we call this paraxial approximation. This means that it's almost nearly normal instance. Okay, so that we don't struggle with this factor because this factor is so difficult to do integration. Okay, so take out this factor and put it outside. Another thing is that this the 1 over R low, that is quite long compared with the actual size. Then let's also take it out and put it outside. So we only have to focus on this phase factor because the phase usually vary much faster than the amplitude. This is a struggle, but this is a very good approximation. In the early days, people can continue to explain diffraction patterns. Okay, the diffraction patterns, like this one. Look at this one. This is a diffraction pattern, and apparently, yes, the aperture size here is much smaller than the distance. That's why you take out these two outside. Because this aperture, the size, the slit is like 100 micron. But this is about meters. So take it out. And this integration basically is the integration over this aperture. Remember that this is surface integration. You only open a small hole here. So this integration is over like 100 micron aperture size. Look at this. And 100 micron aperture size compared with this meter long, this is nothing. Take it out. So this is the why the diffraction theory can be so successful. Because in practice, this can be taken out, and we just deal with this. All right, so if we know this integration, this phase term over this aperture, we know everything about diffraction. It's a very compact expression. Okay, the difficult part is this. If you look at R and low, wow. You have quadratic terms, linear terms. Even though you have very compact expression, it's tedious when you do the integration. Okay, so let's try to simplify this into linear term. and also quadratic term. And if we include the linear terms only, then we call it Fraunhofer diffraction. That is a far-field diffraction. And then if we include the quadratic term into this calculation, then we call this Fourier diffraction. All right, so let's further define rho prime r prime. That is the origin to the source location and origin to the field point. Okay, and if you know the coordinates, it's easy because now, basically, now you put this point, we move this point to the origin. So you set capital X, capital Y, capital Z to be equal to 0. So just set this to be equal to 0, 0, 0, 0. Then you have rho prime and r prime. Okay. So you have this calculation based on the coordinates, because you are calculating everything relative to the origin. Okay. So it's an easy calculation. All right, now it's time to put this and this into the phase term, into the basically want to do this calculation. So we need to figure out this R rho relative to the origin. Okay. So let's do it. So you start to do tile expansion. Rho and rho prime, we just have rho and rho prime, right? Let's relate them through the tile expansion. You see the linear term, quadratic term, and then with tile expansion you have even more higher order terms. Do the same thing for R. Do the same thing for R relative to the origin. Okay, relative to the origin R. Then you have linear term, quadratic terms. You start to heat this. Shukai. You start to heat this, right? Alright. Then whatever you hate, you just delete it. Right. Then however the terms you really hate it, then you delete it, take it out, put it into this, and you start to organize the linear term here. Proportional to capital X and Y. Remember, capital X and Y is a coordinate on this screen describing this aperture. So you organize it into linear term, quadratic term. And you identify that your L0 is an angle along X direction. This is this one. And then you have a point. You have a point here. You take an angle. You have X point here, and then you connect it to the origin and also the source. Then you have an angle, right? This angle. And then along Y direction, along Y direction, this is overlap again. But if you have an extended source, x0, y0 here, and then you connect it to origin, you have some angle. And this describing the angle for the source, extended source here, then connected to this origin, you have instant angle. And then this one, remember this x, y is describing this point P, right? This x0, y0 describing the source. So if your point P has a finite size, then this also defines an axis angle. So you see this L0, M0, L, M, describing the instant angle and axis angle. And this integration is across this surface, this aperture. Okay. So if you take out this, Sukai hate this, then let's take it out. And just put this into this equation. Then we call this Fraunhofer diffraction. If we add these two terms into this equation, then we call this Fourier diffraction. this is the calculation we want to do. Right, so from Hall diffraction, let's take out the quadratic terms. Right? We all hate them, but then we need to put back when we talk about linear diffraction. For now, I'll just simplify it. And if you take out this, then you only keep the linear term, these first two terms. Then you put it into this calculation, and you realize that in fact this is a Fourier transform. Okay. So this is the aperture. You integrate over some aperture, so you can put the aperture function here and integrate from minus infinite to infinite. Previously, you only integrate over this area, this opening area. Now, let's change it to minus infinite to infinite and put the aperture function here. And then copy this linear phase term into this location. You realize this is a Fourier transform of the aperture function. And this is exactly the formula we use when we did the calculation. Let me take out the wrong wheel. This is the starting point, right? So we talk about the slit diffraction. Remember that this is a slit one line source. And then up to this point, we say that, hey, we are doing what? We are doing Fourier transform of the line source. So remember this. So we are not putting something new. We are sort of refreshing the memory. When you do this in the file zone, you are doing Fourier transform of this line source. What else? I think we somewhere, for this one, you're going to see that in fact this is also the Fourier transform, superposition of two Fourier transform of the aperture function. Okay, we did this calculation because the square function, the Fourier transform of the square function is what? Sinc function, right? Fourier transform of the square function is a sinc function, and that is why that's for the slits. For this one, do you see a sinc function? Yes, you see a sinc function. This is a sinc function. Show all right? Right? Yeah, because we have a slit. That is a square aperture. So you see a sinc function. And last one day, I can even generate diffraction pattern from my finger. So let me try it. Well, I'm not that good anymore. Yes, you see sinc function. It's on the opening of my finger. This is a sinc function. Yes, you saw it. Don't pretend you don't see it. Anyway, occasionally I can do it. Need some practice. And this is almost the same function. I want to struggle. So that sometimes I don't have this stick with me. I use my finger to show you the same function. Okay, so we're not talking about something new. We theoretically derive this result, but in fact we talked about it quite some time ago. All right, so if you just retain the linear term in this expression, then in fact you'll be doing the Fourier transform of the aperture. And from the possible theory, everybody knows about this, that when you do the linear system or the Fourier transform, the energy is conserved in the spatial domain and also in the in the time domain. So you have this relationship. So with this, you can use it to do normalization. Okay. So you can do, once you do the normalization, if you integrate this actual function and make it to be the area of your integration, then once you normalize it, the theory will give you this normalization factor based on a real intensity in your experiment. So this is practical. If you know the intensity of your source, then this